Okay, as promised, I'm back with Stan Gibilisco. We're going to dive right into the diode rectifier section here. If you missed the last video, please go and check it out. It'll give you a good context for what we're doing here. The other day, I reviewed Stan Gibilisco's Teaching Yourself Electronics. As I mentioned in that video, I'm very fond of this book. It's a book that's laid out for self-education. So it's basically laid out like a course. It has quizzes, it has tests, and we'll likely go through a lot of those here. But as I stated in my last video, I want to make this really our primary text for learning electronics hereafter. So the first step I want to take here is to cover the diode rectifier section. The reason for that is in other previous videos I mentioned about us taking some time and maybe, designing or building some of the projects that you might want to have on hand if you're going to do electronics. So one thing I mentioned is, hey, if you're getting into electronics, well, why don't you build your own power supply? Because for circuits, you're always going to need a power supply. So instead of buying one, or even if you have one, see if you can build your own, because that's a great way, simple way to start out with electronics. But to be able to design a power supply with you guys, we've got to understand a little bit about power supplies. So we're going to take some time here, and what we're going to do is I'm going to read through, it's just a short section, it's like a page and a half. We're going to read through Stan's explanation of rectifiers, and then we're going to go over, let's see here, we're going to go over some rectifier circuits that I have laid out here in LT Spice. If you're not familiar with what LT Spice is, it is a basically like a simulator for electronic simulator for electrical engineering design. Okay, so what you can do here is you can map out circuits and then you can test it. You can run it through and test parameters. It's basically like having a virtual lab. It'll show you the voltages. It'll show you your readouts for your signal readouts. That's particularly how it's used. It's like an in-computer oscilloscope for simulated circuits. So I have the primary linear or analog kind of circuits that you would find for diode constructed rectifiers. Okay, these are going to be your three most common, and we're going to go through why they exist, when you would use them, and how they work. Okay, so before we get there though, let's have a little chat with Stan and see what he says about diode rectifiers. Okay. Rectifier diodes are available in various sizes, intended for different purposes. Most rectifier diodes are made of silicone. Now, what we're going to do here is we're going to highlight throughout this. This is part of why I want to do this with you guys, because we're going to pick out the important information that you'd want to know about. So they're made out of silicone, are known as silicone rectifiers. Some are fabricated from selenium and are called selenium rectifiers. Two important features of power supply diodes are the average forward current. Let's highlight that. Average forward current and the average forward current rating, and the peak inverse voltage rating. And we'll talk a little bit more about that. He's going to get into it a little bit more, and that's one of the terms I want to cover with you. So let's go into the average forward current. So electrical current produces heat. If the heat through a diode is great, the heat will destroy the PN junction. So you can basically destroy the diode if there's too much heat. When designing a power supply, it is wise to use diodes with an average forward current rating of at least 1.5 the expected average forward DC current. Okay, so this is great. Right offhand here, what he's doing is he's giving you some rules of thumb. So we'd want to have that kind of in our heads about things that we want to know as rules of thumb. Okay, so if we needed a rule of thumb here, would be oh, that came out way too big. Let's see. So one rule of thumb would be 1.5 times your current. I can put C there just for people that are unfamiliar, but you know, current is typically noted with an I. Okay, so 1.5 when you're designing your power supply. Now that's 1.5 of your expected. Okay, so it should be basically the idea is that it should be able to handle 50% more than the total. Okay. So we can keep continuing here. Let's keep going here. If the current is 4 amps, for example, the rectifier diode should be rated at 6 amps or more. Note that the current flows through the diodes. The current drawn by the load is often different from this. Also note that the average forward current is an average figure. The instantaneous forward current is another thing, and that can be 15 or 20 times the average forward current, depending on the nature of the filtering circuit. Some diodes have heat sinks to help them carry the heat away from the PN junction. A selenium diode can be recognized by the appearance of a heat sink, which looks something like a baseboard radiator built around a steam pipe. Diodes can be connected in parallel to increase the current rating over that of an individual diode. Okay, so that's kind of another important rule of thumb here I'd put in here. So if this is 1, you can't see that. Let's go here. There we go. If that's 1, then let's put 2 here. And that was paralleling diodes. So I'll put D in pair. Will increase current. Just put increase I. Okay. And I'll put this in parentheses. D for diode. So a diode in parallel. Let's see if I can get this a little cleaner here. A diode in parallel will increase current. Another rule of thumb that might be important for us to keep in mind. And And I think I'm going to go ahead and highlight that as well. Let's see here. When this is done, a small value resistor should be placed in series with each diode in the set to equalize the current. Each resistor should have a value such that the voltage drop across it is about 1 volt under the normal operating conditions. Okay, peak inverse voltage. This is another topic that's going to be pertinent to not so much our understanding right now of the topology of these circuits, which we're getting into now if you're seeing that, but it gives you a reference into how diodes function. So the peak inverse voltage of a diode is the instantaneous reverse bias. I'm going to highlight that because that's an important topic, not just for diodes but also transistors, because transistors are just diodes anyway, right? A peak the instantaneous reverse bias voltage that it can withstand without the avalanche effect taking place. So the avalanche effect, basically what he's talking about there is, let me see, I went, no, don't want to do that. Basically what he's talking about there it is. What's he talking about with the avalanche effect is basically the breakdown voltage that might happen with the diode. We've talked about diodes before, but we can talk about this briefly here. The deal with the diode is that, remember, the diode is basically like a one-way valve, right? Diode's like a one-way valve. The symbol looks like this, and typically we're going to have a current going that direction unless there's some kind of phase within its operation, which there usually is, especially with a power supply, that you might basically get, you can call it feedback in the other direction. So, or when the voltage is at a different cycle, it might want to come back, and that's why you have diodes anyway. But remember, just because the diode blocks that voltage doesn't mean it doesn't see it. It still sees that voltage. It experiences that voltage, although it doesn't let it pass through the other way. But at a certain point in that cycle, when that energy is going from this end of the diode to this end of the diode, there's going to be potential feedback from the circuit that is connected to that will want to push back into the diode in reverse, what's called reverse bias. So this would be called forward bias. Again, so this is the way we naturally tend to think of diodes. That's why they are pointed in that direction, because that's telling you that this is where that's the direction your current's going. Okay, but in the case of reverse bias, it would be a current pushing the other way, trying to get through the diode, and the diodes have a breakdown voltage. They are rated with a breakdown voltage for their reverse bias, for their what we're talking about here, which is the peak inverse voltage. So meaning that there's only so much voltage that the diode can stand in the other direction. So that's a limit that we have to think about when we're designing and picking out components. Okay, that your peak inverse voltage will be concerning, because when that energy wants to push the other way, we have to make sure the diode doesn't break down in avalanche, like he's saying, which is basically saying that it'll ramp up basically in the other direction, right? So you'll have that energy that's supposed to be blocked, but if it's too powerful, basically it'll break down the diode, and then energy will ramp up in the other direction. So a good power supply has diodes whose PIV, that's peak inverse voltage rating, are significantly greater than the peak AC current voltage. Okay, so that's another, if I have space here, let's see. That's another point we want to make. So let me get my color back here. So 3 would be PIV greater than, I'm going to put here, I'm going to put peak to peak voltage here, greater than peak to peak voltage, we can say. Greater than, okay, so your PIV should be greater than peak to peak. And that kind of makes sense, right? We don't have to think that much about that. That kind of, does that make sense to you guys? It's like you want your limit, your reverse bias limit, to be higher than what your peak voltage would be. So if we were using 120 volts, we want that breakdown voltage to be like somewhere like 200 volts. Okay, so there's no chance of that, because you know that 120 volts can spike and all kind of things, right? Especially when you just turn things on, or if you have a large capacitance reservoir, then your 120 volts, it could go up to 160 and stuff like this. So you get very close. So you want to make sure that breakdown voltage is much higher than the voltage you're actually desiring or operating at. All right, let's continue here. So let's highlight that. That's another good point. If the PIV rating is not great enough, the diode or diodes in the circuit conduct for a part of the reverse cycle. Exactly what we're talking about. That's what I was talking about here with the avalanching and the breakdown voltage. This degrades the efficiency of the power supply because the reverse current bucks the forward current. Okay. Diodes can be connected in series to get a higher PIV capacity than a single diode. Another point we might want to keep in mind. So another thing I would add to that is that, and I wasn't going to talk about this today, but it came across my mind a couple times, that putting diodes in series will also keep your current more consistent. So that's another thing. We'll go into voltage regulators a little bit, actually. I was going to mention this later, but you know, after this video, since we're doing this in heat of building a power supply, it's likely that we'll have to put a voltage regulator in the power supply. I wanted to stay away from doing that just because it would be simpler not to have it in there, but for utility's sake, it would be more beneficial to have it in the circuit. So we'll probably, which voltage regulators aren't that complex at all. So I'm trying to keep it simple, but at the same time, they're pretty simple anyway. So we don't have to, you know, we'll take some time and go over some voltage regulators. But a simple way to, I wouldn't say replace a voltage regulator. The nice thing about a voltage regulator is typically because you usually use an adjustable voltage regulator. That's what's so nice about them. So you can put a turn pot or a trim pot on there, like a potentiometer, a small potentiometer, and you can dial in exactly where you want that voltage to be, and it'll stay there basically forever, right? But putting diodes in series can give you a more consistent voltage, but you can't, you know, it's not necessarily, it's not regulated, right? But it'll give you more of a consistent voltage. But he's saying here also that D in series will give you a greater peak inverse voltage. So that's another point to consider. And what do we have here? Let's highlight that. This scheme is sometimes seen in high voltage supplies, such as those needing tube type power for amplifiers. This is true. High value resistors of 500 ohms for each peak inverse volt are placed across each diode in the set to distribute the reverse bias equally among the diodes. In addition, each diode is shunted by, that is connected in parallel with, a capacitor 0.005 microfarads or 0.1 microfarads. Half-wave circuits. Okay, this is what we're going to get into later on. We're going to see this pretty soon here in a couple minutes. The simplest rectifier is the half-wave rectifier, and this is this one right here. At the A right here is the half-wave rectifier. It has a single diode that chops off half of the AC circuit or the AC cycle. The effective output from a power supply that uses a half-wave rectifier is much less than the peak transformer output. Okay, so that's definitely something we want to keep in mind. The effective output is less than what that transformer can put out. The peak voltage across the diode in the reverse direction can be as much as 2.8 times the applied RMS voltage. Most engineers like to use diodes whose PIV, that's peak inverse voltage rating, are at least 1.5 times the maximum expected peak reverse voltage. Therefore, the half-wave rectifier circuit, therefore in the half-wave rectifier circuit, the diodes should be rated for at least 2.8 times 1.5 or 4.2 times the RMS voltage that appears across the secondary winding of the power transformer. Another good rule of thumb. Number 5. I'm going to put half wave. Put rated. I'm going to put 4.2 times. I'm going to put your. He's using. I'll do it just to be consistent with him. I'll put RMS. We haven't talked about RMS voltage, but that's just your root mean square. We can talk about that in another video. Half-wave rectifiers have shortcomings. The first, the output is difficult to filter. This is an interesting one. I wanted to talk about that. We'll just keep that right there. The second is that the output voltage can drop considerably when the supply is required to deliver high current. Okay, so we're going to talk about that later, but yeah. So your half-wave rectifier, where'd it go? There it is. Oh, jeez. Your half-wave rectifier is going to be poor at collecting current, as pulling current. It's also going to be harder to filter The reason why it's going to be harder to filter, and we'll maybe go into this later more in detail, but it's actually an interesting thing, is, let's say at least in North America, most of the time the frequency of your voltage is at 60 hertz. When you use something like we're going to see later on, which is a full wave rectifier, not a half wave, but a full wave rectifier. When you use a full wave rectifier, that's 60 hertz because both halves, you'll see this, it's called a center tap transformer, because you're using both halves of that transformer and they're basically being combined. Your frequency is going to be 120 hertz. It's actually going to be higher. And it's going to be easier to filter the power at 120 hertz than it is at 60 hertz, right? So basically, the lower the frequency, that it can be more difficult to null out the noise. But having the higher frequency actually plays to your advantage when you are filtering circuits, because it's easier to get rid of. Okay, second, the output can drop considerably when you put a supply at a high current. Okay, we talked about that. So it's bad with current, bad with filtering. Third is the half-wave rectifier puts a strain on the transformer and the diodes because it pumps them. The circuit works the diodes hard during half the cycle and lets them loft during the other half. Half-wave rectification is usually adequate for use in power supplies, in a power supply that is not required to deliver much current. Let's highlight that so we know that. Again, rules of thumb. What we're trying to do is we're trying to conjure up, basic principles and knowledge about, about different types of topology, so we would know what the pros and cons, the advantages and disadvantages of them are. So when we want to build something, we can, use the knowledge that we have, these kind of key principles to guide us, okay? So half-wave rectifiers are inadequate, or usually only adequate for power supplies that do not require the delivery of much current, so low current supplies, or when the voltage can vary without affecting the behavior of the equipment connected to it. The main advantage of a half-wave rectifier is that it costs less than sophisticated circuits. This is true. I was going to go into this later, but we can talk about it a little bit now. There's usually not much of a reason why you would use a half-wave rectifier other than you want to save on costs and just make it simple. And of course, like he said, if it's a negligible thing to input into the circuit, meaning that nothing's going to suffer from it. I think in one instance, this comes across when I think about this is with guitar tube amplifiers in particular. If they're using what's called a fixed bias for the output tubes, they'll often use basically a half-wave rectifier for the negative voltage that needs to be placed on the grid of the power tube, because as he iterated here, so the bias doesn't take a bias for a vacuum tube is current based, or it's voltage based. It's not current based, so it's not going to take very much current. So the half-wave rectifier is fine. And that makes it also very simple for us too, right? And on top of that, again, it doesn't need very consistent voltage. They can fluctuate. Let's say it could probably be plus or minus 2 or something like that, for a fixed bias on a guitar amplifier. So that's the situation in which having a half-wave rectifier would be fine. So let's talk about the full wave rectifier. And here you're kind of, well, we'll talk about the picture in a second. Sometimes the only thing that, I've noticed about this, sometimes the figures and the illustrations come before the actual explanations. But at any rate, a full wave rectifier center tap circuit, a better scheme for changing AC to DC, takes advantage of for both halves of the AC cycle, both halves of it. So what he's talking about here, okay, let me get my pointer out here. So what he's talking about here is this is the full wave rectifier here, okay? That's the full wave rectifier. What do you notice about this circuit that you don't see, or that you see in this circuit and you don't see in this one? Okay, this circuit here, if we can see, has some things missing in it. Because there's this interval here that's basically the negative. This is basically the negative, what would have been the negative cycle of the AC. Because right now, what do we have here? This is an illustration of AC going into here. So it was like this one was going in, right? That's what it was, and this is what it became, okay? You can see that it cut off, it did part of the job for us because it cut off the negative. But now the negative just disappeared, and now you only have DC. This is unfiltered DC, okay? Now you only have DC on the positive cycles, and only half, and you only get that every other period here, right? No good. I say no good, but that's actually why it doesn't pull current very well, okay? This is exactly why, when we just talked about that, this is exactly why your half wave isn't going to pull as much current, because it only takes half the wave. Again, if we have an AC, this is an AC circuit here too. This is all AC going in here. This is AC going in here. Your half wave only pulls in half of the cycle, where your full wave is going to take the whole thing. That will make it better at pulling current than your half wave will. Oh. Clicked one too many times here. Okay, so back to the full wave here. So the full wave center tap, it'd be better at, it has the advantage of using both cycles. Half the full wave center tap rectifier has a transformer with a tapped secondary. We'll see that in the illustration here. Where is it? Right here. Okay, so that's a tapped secondary. If we see this, remember we have our transformer. This is the primary, this is the secondary, this is where our AC signal coming out or coming in. This is where our DC signal is going to come out. As you see, you can see that annotated here, because this is not annotated with anything, because this is AC signal. This has the positive and negative on the other end. Now, what do we find different about this one here? This would be the full wave rectifier here. What do we find different about this? With the full wave rectifier, there's a separate. So we use a transformer with a center tap. Now you've got to use a transformer with a center tap for this to work. And we'll get into this more later. But that's your full wave rectifier, And what it's doing, what it's going to do is it's going to use basically, it's going to see this transformer, this secondary, almost as two different transformers. And one diode is going to use one half of it, and the other diode is going to use the other half, and that's how you utilize the full cycle here. The center tap is connected to electrical ground, also called chassis ground. This produces voltage and current at the ends of the windings that are in phase opposition with their respect to each other. So they're out of phase, which I was just talking about. So you have to. That's why you have to have the center tap. You center tap it, which basically means you ground it. So that's your 0 point, and you're going to have negative voltage and a positive voltage on each of those windings. These two AC waves can be individually halved, individually half wave rectified, cutting off one half of the cycle and the other over and over. The effective output of the power supply that uses a full wave center tapped rectifier is greater relative to the peak voltage than in the case of the half wave rectifier. Okay, let's make note of that. The peak inverse voltage across the diode can nevertheless be as much as 2.8 times the applied RMS AC voltage. Therefore, the diode should have a peak inverse voltage rating of at least 4.2. So we can see that the same principle still exists for 4.2. So that's something, again, that's why we have these rules of thumb, because they'll likely keep us good in every different scenario. So we don't have to, remember a whole bunch of different things. The output of a full wave rectifier, a full wave center tapped rectifier, is easier to filter than the half wave because the frequency of the pulsation in DC ripple from the half waves is twice the ripple frequency of the pulsating DC. Okay, remember that's what I talked about here. What he's talking about here, I think a shame perhaps that he doesn't give you any numbers here, but just like I said, so this is going to be, and we can go up to this diagram again briefly and look at this. What happens here is that your 120 here, your 120 volts here, that's at your input at 60 hertz. It's still going to be 120 here at 60 hertz when it comes out, lower frequency. Here you're going to have 120, 60 hertz, but then you'll have your 120, and then you'll have 60 hertz here, and you'll have 60 hertz here. Because these two are going to be combined at the end, you'll have 120 hertz here, which in turn makes it easier to filter. Okay, so that's the magic by using this, which is really nice consequence of using the center tapped full bridge rectifier. So you're not only going to get higher current, you're also going to get a power supply that's easier to filter. Okay. Okay, so if you compare figure 1, or if you compare figure 21 2B with figure 21 2A, you will see that the full wave rectifier output is closer to the pure DC than the half wave rectifier is. Another advantage of the full wave center tap rectifier is the fact that it's gentler on the transformer and the diodes than the half wave rectifier is. Yet another asset, when a load is applied to the output of the power supply that uses a full wave center tapped rectifier circuit, the voltage drops less than in the case of the half wave rectifier. That's what I was going to point out earlier too. So you'll get more voltage also, and you should get more of a consistent voltage, but you'll get more voltage out of the full wave rectifier as well, because there's less of a voltage drop. Because of the transformer is more sophisticated, the full wave center tapped circuit costs more than the half wave circuit that delivers the same output voltage at the same rated current. So, and I like what he's doing there is basically inputting the cost of the transformer into the circuit, because you can't make the circuit without the transformer, right? So that's a good thing to keep in mind here. And he's saying that, hey, well, if you have a situation in which you can get the kind of current you need from a half wave rectifier, you might as well just do it from a half wave rectifier, because it's going to cost you less for a transformer. Just as in the case of when I was talking about guitar amplifiers that use fixed bias and that need a tap for negative voltage, usually they're tapping that on the transformer that's already existing. They're not putting in another transformer to save money, essentially. Full wave bridge circuit. Okay, so this is the last one that's going to be on our list here. So another way to get a full wave rectification is the full wave bridge rectifier, often called the bridge. It is diagrammed up top. We'll look at it soon. The output wave is similar to that of the full wave center tap circuit. The effective output from the power supply that uses a full wave bridge rectifier is somewhat less than the peak transformer output. And the peak voltage across the diodes in the reverse direction is about 1.4 times the applied RMS voltage. Therefore, each diode needs to have a rating of at least, let's say, 2.1 times the RMS voltage that appears for the transformer secondary. The bridge circuit does not require a center tap on the secondary. It uses the entire secondary winding on both halves of the wave cycle, so it makes even more efficient use of the transformer than the full wave tapped. The bridge rectifier also is easier on the diodes than the half wave rectifier. There are some points I want to make about that. Full wave rectifiers tend to be used, yes, quite a lot, but it also depends on your needs for voltage, and we're going to get through that, I think, in the next video, because we seem to be not running out of time, but we're getting up there in time, and I don't want to make this video will go and be an hour and a half, or 2 hours if we keep going. So a good 45-minute stop is good for us. I hope you guys appreciated that. Let me just take a look real quick here at the circuit so remember what we're looking at. Almost forgot to do that. So this is the half wave. So before we go, this is the half wave, this is the full wave, and this is the bridge, okay? And they're kind of in order of sophistication, also in the order of voltage performance, and we'll talk about these respective to the LT Spice circuits that I have laid out here. Okay, we'll talk about that in just a little bit. But for now, I'll bid you adieu, and in the second video, we'll cover these in more detail, and then we'll do some simulations and kind of see how they all work and all that. And that'll get us primed to start building our own power supplies. Thanks for watching. I'll see you soon.